Good afternoon, everyone. Thank you for joining us for our fourth webinar of the year. My name is Rob Farrell, and I'm the Director of Research and Development for NOARK North America. I'll be kicking off the presentation and giving you a little bit of background on the company. This is an interactive session. We'll explore the new series of variable frequency drives that NOARK is currently introducing. The key topics for today are very basic: how drives work, the fundamentals behind their construction and design and their operation. We'll be reviewing some features and benefits, and Jason will be providing us with some real world applications later on. I'll let these gentlemen introduce themselves. Our speakers today are Jason Smith and Keith Pierce, both with many years experience with drives. So I'll give you an introduction to the company. NOARK is a subsidiary of Chint, the Chint Group. Chint has been Chint is one of the largest electrical product manufacturers in the world, with over $22 billion in sales. We have 50,000 employees operating in 140 countries around the world. The company began in 1984 and has been focused on the IEC markets in Europe and Asia in the early stages of its growth since then. And then in 2012, the NOARK subsidiary was created and founded in Europe and in the United States. So our North American headquarters is in a suburb of Dallas, Texas. We just moved there earlier this year. The purpose of having a separate brand under the NOARK name is really to provide emphasis on the UL listed products that we need for this market. So if you look at the parent corporation under Chint, Chint essentially makes every electrical product that is within power distribution and control across the board. So everything from a miniature circuit breaker in a residence to high voltage transformers and dead tank circuit breakers at the other end on the utility and transmission and distribution side. So Chint has all of those products primarily under the IEC listing and certifications. And the purpose of NOARK is to introduce and support UL listed products in North America. So we began with OEM products, mainly components of low voltage circuit breakers, motor control products, and so on. And now we're expanding into more assembled products, low voltage switchboards, panel boards, and bringing in transmission and distribution products like pad mount transformers and high voltage transformers. So that's kind of an overview of the history of where we came from. And the tagline that you see here, excellent products, exceptional value, that really summarizes the approach that we've taken to the North American market. We manufacture high quality products and we offer them at competitive prices. We're not afraid to put inventory in North America. So over the last 5 years, we've seen some substantial growth in North America, and primarily because of the really good quality of the products, but also because we've invested in inventory and in supporting a fully stocked warehouse in both, and now in Dallas, and we have a Canadian warehouse in Kitchener, Ontario. So really, this is what we're all about. The new drive product we're going to talk about today is no exception. It is truly a world-class product that we'll be introducing to you all in the next hour or so. If there are any questions, you can post them in the chat. Or we'll leave time at the end for direct questions as well. Without any further discussion from me, I'll turn it over to Keith to start the training.
Thank you, Rob. Good afternoon, everyone. My name is Keith Pierce. I'm a regional sales engineer. About 30 plus years of experience with drives at some of the biggest companies in the globe. What we're going to talk about today and some key topics that we want to discuss and review. What VFDs are and how they work, basic fundamentals behind them, what key components are in a VFD and what their function is. Features and benefits, we'll talk about those as well, and why would I want to use a VFD? You know, the key components of a VFD and stuff, we don't want to get too technical. Some of you guys may be at beginning stage, and some of you may be more developed with your skill set. But we'll hit on some basics, make sure everybody understands how VFDs work and what we can do with our solution that we're offering and bringing to the market. About 65% of the global industry is industrial electricity is used by motors. And 80% of those cases, motors are oversized, causing a lot of inefficiencies. You know, so what can drives offer to the market that help reduce these inefficiencies? We already know it's a big use of the electricity, and now we're going to dive into what we can do to save on that electricity. A variable frequency drive, also known as a VFD, controls the speed and torque of an AC motor by varying motor output voltage and frequency. Some of you may have known or heard of a VFD also as adjustable speed drive, ASD, variable speed drive, VSD. Sometimes the word frequency is put in there for speed, inverter drive, or AC drive. All common names that are used in the industry. The primary purpose is to improve process control. You get a lot of energy efficiency from using a VFD, and you also extend the motor and the equipment life. If you are using older technologies, you may go like a starter from 0 to full speed in a heartbeat, and that's hard on the motor, that's hard on the mechanical, and that's also hard on the utility. So VFD solves a lot of those problems. How VFDs work. Basically, AC input power comes into the drive, goes through a section called a rectifier, to a DC bus, to an inverter, and that goes output of the drive and controls the output. Now, normally on your input, you're used to something that looks like this, AC for voltage and current. Well, through all the processing that's done in the drive, this is what it comes out to as far as the voltage out to the motor. And this is what comes out relatively looking like that for the current. One of the common things I hear is people will take a voltmeter and measure the output of the drive to see what voltage is outputting. And sometimes it'll be higher than the input voltage. You say, how can that be? This thing's making energy. Well, it's really not. Your meter is trying to interpret this square wave on and off, and it doesn't do a good job. There are a few meters out there that do a very good job. They've got some filters and stuff, but overall, this is what actually goes to the motor. Control methods. We have volts per hertz or frequency. You have an open and closed loop vector torque control, which is going to be for more precise applications where we have to regulate torque. Open means there's no encoder feedback, and closed means there is. With the close, you get better performance. But most of the applications, just volts per hertz is going to be, or sensorless vector, I forgot to add that in here, are other options for control. So this is an electrical diagram of what a VFD actually looks like inside. We've got up here, we talk about the rectifier. So this section here, AC power comes into these three terminals, this section right here, and you can all see my mouse, correct? So that section here is actually going to be with a diode called the diode bridge. On bigger drives, they might be SCRs. And we basically rectify the voltage to make the DC bus voltage, which has our capacitors. This is symbolizing the capacitor section. It could be multiple and probably has multiple capacitors. And then this section out here is called the inverter. These are the transistors that are also commonly known as IGBTs. So these are utilized to fire on and off the bus voltage, which is a DC voltage, to the motor. And how we vary that on and off sequence controls the speed that goes to the motor and makes the motor run at different speeds. So this is kind of a recap of that section with a little bit of graphics. You got the rectification section, which is, this is the sine wave coming in 3 phases. It rectifies it with the capacitors and sometimes an inductor. It smooths this out. And then again, the inverter turns on and off to put this PWM square wave out to the motor. And that's what makes all the magic happen. Wiring connection diagram. So in the drive, just like any other drive you've ever worked on or worked with, you've got your fusible disconnect or, circuit breaker or fuse disconnect switch. We've got the input power. We've got the motor connections with a ground. We've got all the digital inputs that are used to start, stop, maybe do preset speeds. I want to run at this speed and that speed, and I change those inputs. You just program them accordingly. And various other functions are done with the digital inputs. The analog inputs could be a potentiometer, which varies the speed of the drive if you tell the drive to look at that analog input. Let's say a potentiometer here is wired to analog input 1. It takes the 10 volts and varies that from 0 to 10 volts, and that makes the drive go from 0 to full speed. We have an analog output here, which can be set up for different things. Voltage and current basically telling you, yes, we are running at that speed, and maybe what load is actually being drawn. It could be a 0 to 10, it could be a 0 to 20 milliamps. We also have a digital output that is, it's like a relay, but it's just a digital output. It puts out a voltage and then indicates what's going on with whatever we programmed it for. We also have relay outputs. The relay outputs could be, I'm running, I'm stopped, I'm faulted. And you have that power go back out to lamps and tell you, pilot lamps, and tell you that it's running or not or faulted. We also have a Modbus communication that is standard on the drive, RS-45, that the drive can be wired to a PLC or a SCADA system or something and be told to when to start, when to stop, when to run, what speed to run. If I'm faulted, what my current is output. You can gather all the data out of the drive and bring that back to another system. And like I said here, communications is for control and monitoring. Let's see, what else was there? There is a CAN bus up here that we'll talk about a little bit later. And we've got braking resistors and braking units if needed to help take care of excessive energy. And we talked about it before. The I/O terminals typically are 24 volt DC level. In my previous lives, I've seen 115 volt control. More global, it's all went to 24 volts DC. We have a 4 to 20 milliamp output or an input. We have a 0 to 10 volt DC for the same scenario. Features and benefits of our drive. These are hardware and firmware features, easy to program with logical parameter grouping. The hardest thing anybody does, and again, I've worked with a number of different drives in my lifetime. The hardest thing is always the beginning, understanding how a manufacturer sets up the parameters and what I need to go do and all that. We've done a pretty good job logical grouping of the parameters to try to make it easy for you. I know in a short period of time, it'll be very easy for you. Flexible I/O, we can configure it to numerous different conditions that'll help for your application. There's an automatic adjustment of the volts per hertz curve to provide better torque or energy savings. The one that I've seen a lot of recently is the automatic carrier frequency. A lot of manufacturers don't have that. And that gives you better performance. They monitor that for thermal protection to make sure we don't overheat the transistors. And it also reduces the audible noise. I was at a customer running a compressor, and some of their folks came by and did not believe the drive was running. It was that quiet. So normal singing will be minimized with our drive. It'll be quieter. Can handle 2 motor configurations can be stored in the drive in case you have a process that you got to jump from one to the other. You can set that all up and then just by a digital input toggle between which one is being utilized. We talked about the brake chopper to take care of regenerative energy. Not all applications need that. We can also add pump control firmware or replace the firmware that's in the drive with pump control firmware. Adds a ton of pump features. We can get you a document that'll talk about those features as well. What this helps is you don't need to add a PLC. You can reduce the cost of your enclosed package by removing the PLC because a lot of those features are in the drive associated with pumping applications. CAN bus master-slave communication for peer-to-peer pump control. That's for multiple drives working together in a coordinated system. We've developed that inside the drive. And it's not really utilized. Some of the slides, unfortunately, talk about open. It's really not an open protocol yet. We're working on that for the next generation. Open and closed loop vector, we talked about that earlier. One of the other big things that I think is really becoming popular is a permanent magnet synchronous motor control. We can run permanent magnet motors. I don't think a lot of drives have that capability. That helps with unique applications that are trying to do special motor applications, maybe to reduce a gearbox. We've controlled the 28 step motor, or I shouldn't say step, pole motor. And that allows that customer to remove the gearbox and just has the motor because it's got so many poles it can produce the torque it needs without the gearbox. Saves cost, saves weight, saves failure point. We also do a lot with pump jack functionality. Pump jacks, Jason's going to talk about a little bit later in the presentation, but we have features in the drive that pump jacks will run into and does a great job to do it. C3 level EMC filter is included in the drive because the drive before brought here to North America has been sold for a number of years in Europe and in other parts of the world where EMC noise levels are mandatory to be below a certain level. So we have the capability in the drive to have that component in there, and it will be in there all the time, actually. We're not going to take it out even if you don't need it. It's so much embedded into the drive. The other thing we get into is we put a heavy conformal coating on the printed circuit boards to help with those caustic or humid or moisture-ridden environments. That helps seal the board, the components, so that they don't run into any kind of condensation issues. The benefits of a VFD saves energy. A lot of times today, people will run at a size that's big just to make sure they covered themselves, and it really is inefficient and it keeps, a lot of energy kind of tagged for that application. Better regulation and process control. With traditional methods, you don't have process control. Or if you do, it's pretty crude and is not very efficient. Much better regulation with the VFD. Maintenance costs we talked earlier are reduced relative to smooth starting. You're not going with a starter from 0 to full speed in a heartbeat, which wreaks havoc on your mechanical stuff, your motor, and your line. Reliable start, stop, and synchronization. Reduced peak inrush demand as compared to starters and even soft starters. Soft starters are better, but they're not as low as a VFD. Starting current restricted to 150% of full load instead of 600 for direct across the line. And that's old, that data. Today with premium efficiency motors, I've measured it, it's 800 to 1200% inrush potential. Drive, it's 150% only because if we have to break a load free to get it up and moving, otherwise it's usually 100 or lower. Improved power factor because the drive is between the line and the motor. The motor may have a certain power factor. The drive has its own, so which up to in the upper 90 percentile. So great use of power factor savings. And excellent ROI on variable torque applications, which Jason will talk about in a little bit, capable of less than 2 years payback. So great way to utilize VFDs. And speaking of the devil, Jason, you're up.
Good afternoon. Thank you very much, Ken. Or Keith, sorry.
That's okay.
Yes, my name is Jason Smith. I'm Regional Sales Manager for Western Canada for NOARK. 28 years in automation and control industry, working with most of the major platforms over the years. And I'm here to talk to you about real world applications and some of the challenges you may encounter with some of the implementations and considerations that we need to be aware of. If we could proceed to the next slide, please. So VFDs are present in basically every industry currently that we're aware of, from everything that delivers water and removes our sewage to heating and cooling the buildings, gas compression, conveyors, moving product, people, hoists, escalators, separation. Next, please. VFDs are broken down into two general categories. We have what we call variable torque, and we have a constant torque. In a variable torque, which covers about 80% of the applications in the industry, your pumps, your fans, water, wastewater, heating, cooling. These are considered variable torque applications. We can step into the next. How are we saving energy here? Well, in a variable torque application, you do not require, it needs less torque to start. And it's a non-linear progression of speed versus energy. So we could be running at 80% of the speed, but only require about 50% of the energy to accomplish that. Next, please. Constant torque, however, which consists of about 20% of the applications, compressors, conveyors, mixers, they require constant torque throughout all ranges of its and energy consumption throughout. So it's more of a linear progression of energy versus speed, because you're always going to need to overcome that torque. Next, please. Where we see these commercial and infrastructure applications, we have HVAC systems and building automation systems. They're generally closely tied, but heating and cooling the spaces we occupy, generally keeping it warm in the winter, which is quite advantageous, or cool in the summer. And then moving people, elevators, escalators, providing speed control and smoother start stop. Next, we have them present in marine, oil, gas, and mining applications. Marine, a VFD will be driving the motor that controls the propeller to move the vessel, or used in the dredging. For oil and gas, we have our pumping, compressing the natural gas drills, and pump jacks, which your extraction. Your top left picture there is a typical pump jack where you're going to end up with through the process, it will be moving that up and down and extracting the oil from the ground. Next, please. Things to be considering, common issues you may encounter: harmonics, voltage spikes, and electromagnetic interference. In the harmonics, VFDs draw nonlinear current. They could potentially cause harmonics that distort the power supply and affect other equipment. Common method to overcome this would be using line reactors or harmonic filters. Voltage spikes and motor insulation stress drives generate high switching frequencies, and on long cable lengths can cause voltage reflections. Recommendation is, you use inverter duty motors, move the drive closer to the motor itself, load reactors, DVDT filters, or sine wave filters. VFDs can generate electromagnetic interference and affect your other automation systems or process control systems. Shielded cable, grounding, and filters would help you overcome that. Next, please. Things to consider when you're determining your application. Your drive will generate heat. We need to make sure that we can shed the heat in an appropriate manner to allow it to be reliable operation and maintain a long lifespan. So depending on the instance, our drives here have the capability of, with a kit, being installed by themselves into a NEMA 1 environment. But in other environments, you may need to enclose them. So you will need to consider size of your enclosure to help dissipate the heat, and any other external cooling methods, venting, air conditioning, fans, things of that nature to maintain a proper operating temperature. Next, please. Mechanical and motor issues. You end up with bearing currents and torque, ripple, and resonance. You can have shaft voltages, which could damage your bearings, and general recommendation would be to install the insulated bearings or grounding rings. For torque, ripple, and resonance, you could end up causing vibration and mechanical stress due to poor tuning. Fine-tune your control parameters and use open and closed torque control techniques. Next. And then you could run into the power supply and sizing issues. If your application has your drive and motor are undersized for the application that you're using it on, you could end up with nuisance trips or irregular performance. You'll want to review that and determine what the appropriate size motor or drive is, and allow for a reasonable tolerance above that to just maintain the lifespan of the motor or the drive. And then voltage unbalance and sag. which could affect the stability of the DC bus. Power conditioners or line reactors will help mitigate much of that. Next, please. When determining your application, you should take into consideration the compatibility of the motors, any potential power quality issues, harmonics, and any sensitive equipment that would be affected. Of course, heating, and one thing I didn't cover was the altitude. The drives are rated specifically to 3,300 feet, 1,000 meters in altitude. And if you're operating above that, then you would need to derate. The same would be the case if you're operating in a hotter environment. Next, please. When selecting a drive for an application, ideally, getting the motor nameplate to be the best case scenario would allow you to properly size it. But in the absence of that, voltage, amperage, and application would be the key points of information that should be obtained to be able to properly select the appropriate drive. Next, please. When should I consider an input reactor? Well, if you're experiencing stray voltages, spikes, imbalances, or you're running the drive close to its maximum, if there's any harmonics, using an input reactor would allow you to overcome that, would improve your power factor and reduce harmonics. Next. When should I use an output reactor? If you've got long lead lengths and you're using a low impedance motor, using a output reactor would help you prevent any potential spikes and add an additional impedance for proper operation, a more reliable operation. Next, please. So more highlighting the enclosure and environmental ratings. As I noted before, we have the ability to have the drive alone with a NEMA 1 kit, so you could install it on a wall in an electrical room without any need for an enclosure. But if you're dealing with other environments, outdoor water corrosion or extreme amounts of dust, then you'll need to consider enclosures of the appropriate type for those environments to go put the drive in. Next. You may encounter loads, applications where you need to control multiple motors from a single drive. In this application here, we're looking at a drive controlling 4 motors for a cooling fan. Those motors will ramp up and down, speed up and down based on the one drive. In these applications, you would want to size them with adding all the full load current of each motor together, plus about a 10% tolerance. Include separate overload modules for each one, and then program the drive for voltage frequency control. So you can see here we've got a temperature transmitter into a PID loop inside the drive, and that would be varying the speed of the fan based on the temperature input. Next, please. Drives are designed to integrate with most of the common industrial automation and building control systems available through its available protocols, Modbus, which Keith discussed earlier, but Ethernet IP, Rockwell-based protocol, and BACnet, which is a fairly common building automation system. This would allow you to, as Keith indicated, monitor the status of the drive itself, as well as control, and then allow you to to plan predictive maintenance. Next, please. We conform and have all the same standard protections, overload, over voltage, under voltage, over temperature that you would expect to see in a drive, as well as conform to all the standards and certifications required for our marketplace. Next. And here we highlight some of the in point form, some of the various control features that we've discussed, and including smart PC tools for inverter control and troubleshooting, but our sizing as well. So 110 to 230 volts, single phase in, 3-phase out, 0.5 horsepower to 3 horsepower, 230 single phase in to 3-phase out, 0.5 horsepower to 3 again. And then your 230, 3-phase in, 3-phase out, 0.5 horse to 15 horse, 480 volt, 1/4 horse to 250, and 575 or 600 volt, however you wish to refer to it, 1 to 150 horsepower. Just then on the picture in the bottom there, we have the a little programmer module that is available for use with programming the drives from your PC. And we I don't think we've referenced it anywhere else, but we do have STOs available in the drive itself, the safe torque off. Next page, please. We have more of the same. So some of the description of the technology: advanced DSP technology, compact design. So we do size our drives appropriately for the horsepower and voltage that we're working with. Unfortunately, I've encountered in my past lives companies that aren't necessarily doing the same thing. But again, highlighting the NEMA 1 enclosure, communications, and we do have a wide range of accessories, keypads, mounting hardware, or mounting kits for remotely mounting that keypad, and etc. And then next, please. So this is where if you have any questions,